This is a super cheap and rather crappy webcam, and today we are going to show you how we hacked this little thing, so we can see straight through solid metal, almost like it's made of glass. This isn't a magic trick, nor is it some kind of optical alchemy. This is just basic physics, and with a little bit of background knowledge, it allows us to use a webcam to see through metal. This metal is silicon, and today we are going to take a webcam to the very limits of its sensitivity. In fact, we are going to push it to the point where near-infrared and shortwave infrared crossover. We are pretty sure that right now, there are a few people busy writing into the comments that silicon isn't a real metal at all. For some, this material is classified as being a metalloid. You humans have this curious urge to classify things into groups, and have really strict definitions for them. I find this a bit strange, because the universe doesn't seem to give a rat's ass about your rules for each type of classification. So, in this video, I am going to be calling silicon a metal, and I'm not going to apologize for that at all. If you are the chemistry equivalent of a bloody cork sniffer, then have fun in the comments. So, in this video, we are going to explain exactly how and why it is possible to see through a solid piece of silicon using a simple webcam, and we are going to show you how we hacked it. We are certainly not using an expensive thermal infrared camera, or even a mind-bendingly expensive shortwave infrared imager. And don't think that this is just idle curiosity, although there is absolutely nothing wrong with just being curious. You see, there are actually some very interesting, real-world applications for this imaging technique, and we are going to explore a couple of them. Right, let's crack on with it. Just occasionally, our failed projects can be the inspiration for something new and better, something that actually might stand a chance of working. And this is basically the backstory for how this project got started. I don't really want to discuss that failed project. It was poorly conceived, badly researched, and frankly, it was doomed to failure from the outset. But it did call for a 2-inch silicon wafer, so my human assistant eagerly got to work preparing the surface of the wafer. And that's when disaster struck. My clumsy assistant broke the delicate wafer, which actually turned out to be a blessing in disguise. We also got lucky in two ways. Our first lucky break was that we had our old Euler phone to hand. This chunky smartphone has a thermal camera, so we wanted to see firsthand that silicon, like germanium, was really quite transparent to thermal infrared wavelengths. And indeed it is. We had never tried this ourselves with a piece of silicon, mostly because we normally didn't have any conveniently shaped silicon to hand. And this is the lucky part. This particular smartphone also has an infrared night vision mode. For some reason, my human assistant decided to stick this piece of silicon right in front of the camera that is able to see into the near-infrared. And then, we had our second lucky break. It was daytime, and the room was illuminated by strong sunlight. What we saw was literally the spark of inspiration that started this project. The results are pretty low contrast, and fairly blurry, but we were literally looking through a piece of metal, using a simple CMOS image sensor. So, excited by this result, my human assistant and his daughter went outside to capture some images. The results were absolutely fantastic. Today, we learned something new, that the transparency of silicon can extend to the kind of wavelengths that a cheap sensor can see. So, in the immortal words of a certain Martian, we were just going to have to science the shit out of this. As an amateur experimenter, nothing beats testing the theory yourself, and seeing the results with your own eyes. Our spectrometer has about the same infrared spectral range as a typical CMOS image sensor. We are using a halogen bulb as the source of illumination. It doesn't have so much energy in the region of interest, but hopefully it is enough. When we insert a piece of silicon into the optical path, we can see there is a definite peak. If we adjust the gain of the spectrometer to give us a clearer plot, we can see that at about 1000 nanometers, the response starts to increase. In our plot, the response appears to fall again. This is more to do with the spectral output of the halogen bulb being greatly reduced in this region, and not the silicon pass band. So, let's see if our lucky accident can give us some useful results. I think that the first thing we should establish is that the silicon wafer that we are testing really is opaque to visible wavelengths. This is a laser-excited phosphor-based flashlight, and it is very, very bright. As you can see, there is no light leakage visible through this silicon wafer. But we can take this a step further. If we use a laser beam instead, the actual power density can be significantly higher. This violet laser is also apparently completely blocked by the wafer. Next, a red laser that has a wavelength of 650 nanometers. Its power output is only 60 milliwatts, but the power density over the small beam area is around 20 times that of the big flashlight. Once again, nothing is visible through the silicon wafer. Right, let's test this green DPSS laser. Again, it has a total power output of around 60 milliwatts. What the hell is this? Oh dear, that really shouldn't be there. So, what exactly is going on? Well, the first clue is that my human assistant can't see this, it only shows up in the camera footage. Maybe, this is infrared that is emitted by the DPSS laser. This really should be filtered out. Mind you, this is a very cheap laser pointer, and perhaps the filter was omitted. Well, let's find out. We can add an infrared cut filter, and see if that removes this spurious emission. And with the filter added in the beam path, we can test this again. And now our mystery emission has disappeared. Well, that makes this a pretty dangerous laser. There is a very significant amount of invisible infrared being pumped out of this thing. Brainiac would have a bloody heart attack right about now. And that was a very long-winded way to say that silicon is opaque to visible wavelengths. So, let's see why it is transparent to infrared light. Silicon is a semiconductor, which means that it isn't an insulator, nor is it a conductor, it is sort of both. I am going to avoid getting into semiconductor physics too much, and just focus on the properties that allow silicon to be transparent at certain wavelengths. Semiconductors have a property called a band gap. This is sort of an energy threshold where the material can change how it behaves. From an optics standpoint, any photon that strikes silicon with more energy than its band gap will be absorbed, and those with energies below that will pass straight through. Silicon has a band gap of 1.13 electron volts, which when converted to wavelength, results in a threshold of 1100 nanometers. If we look at the spectral response of a typical CMOS image sensor, then that puts the cutoff right here. In theory, our webcam should not be able to detect any of the photons that can pass through silicon. So what's going on? Well, that perfect threshold concept assumes a lot of things, most importantly that the silicon has a 100% perfect crystal structure, and that it is at a temperature of absolute zero. Clearly, neither of those things apply here. At normal temperatures, around 300 Kelvin, the molecules in the silicon are vibrating pretty wildly, due to this heat energy, and this causes the band gap to fluctuate too. Whilst the average band gap energy will be as expected, it means that there is a statistical chance that some higher energy photons will not be absorbed. Fundamentally, this means that the cutoff energy between absorption and transmission will not be a step on a graph, instead it will have a pretty wide transition band. If we take into account the temperature and the typical crystalline properties of a semiconductor wafer, we end up with a transition band that looks like this. We are going to choose an active wavelength of 1064 nanometers, it is commonly used and so the optical components are cheap. That puts us right here on the transmission graph, so about 25% transmission. First of all, we are going to add a band pass filter to our camera, so it only can see the light that has a chance of passing through silicon. It should improve the contrast of our images. We are also going to need a source of 1064 nanometer light to help with the imaging, we can't just rely on the sun. We bought this powerful source, thinking it was an LED, but later we realized it was a laser. My human assistant's Chinese language clearly isn't as good as he thought it was. In the end, the laser turned out to be a happy accident. Right, let's build this thing. Enough of the theory. It's time to convert a cheap and nasty webcam to see through some metal. This little camera is a UVC device, meaning that it can just plug into any compatible product, and you can get video out of it. There really isn't much inside this little camera, so stripping it down was a breeze. Normally, we would start by stripping out the infrared filter from the back of the lens module, but in this case we are just going to replace the lens. We are also going to replace the lens holder, for one that allows a longer focal length. We are trying to make this camera be capable of being a crude microscope, as well as being able to focus to infinity. With a new 3D printed case, we can also fit in the 1060 nanometer band pass filter inside the camera. It is important that this dichroic filter is fitted as close to the CMOS image sensor as possible. The light passing through this filter needs to be as parallel as possible, or the pass band will be different in the center of the image, when compared to the edges. And that is basically it. A very simple conversion process for a very simple webcam. No need for any expensive components, no special focal plane arrays, or any cooling required. Here you can see the lens adjusted for focus at infinity. The images might seem pretty dark, but we are only allowing a very narrow bandwidth of infrared light to enter this camera. And with the lens adjusted to focus at about 6 mm, we can achieve a fairly crude microscope effect. You will see why we wanted this feature a little bit later. And finally, there is our source of 1060 nanometer illumination. It's kind of funny how we bought an LED, and ended up with a laser. Yet another happy accident it seems. Right, let's go look through some silicon. This is a microchip, presumably it is one that has failed testing, and is essentially a waste product of the semiconductor industry. I managed to buy a bag of them for virtually peanuts. And this is the main reason for wanting to make this camera have the ability to be a sort of poor man's microscope. We have placed the laser inside a 3D printed box that also acts as a stage for these chips. The eagle-eyed amongst you will have also noticed that I have placed this die on the stage, upside down. And now, with the laser on, we are literally looking all the way through these chips, as though it was an X-ray image. The aluminium interconnect layers are the dark parts of the image you see. The images aren't perfect, but this is certainly good enough for identifying various structures on the die. Looking at this chip in more detail, I suspect that this was part of a multi-project wafer, because it looks like there are a few copies of each of the designs on this particular chip. This isn't much of a microscope, but based upon the size of the bond pads, I estimate that this illuminated circle is about 2 mm in diameter. Here is another chip. This one doesn't have a polished back face, it is raw from the wafer sawing process. And this clearly has a very detrimental effect on the quality of the image we can obtain. This rough surface causes a lot of scattering, and distorts the image. This is essentially the same as looking through frosted glass, and means that we can only use this technique for imaging dye that have been backlapped. Here is a great demonstration that we are indeed imaging right through the chip. It actually doesn't really matter which way around the die is placed when imaging it. Basically, it will just give a reversed image, the contrast and details that are present are exactly the same. We are using a great free application for capturing these images, called Next Camera. It allows all of the settings, like exposure, gain, and color management, to be set manually. We were so impressed with how well this technique worked, that we have decided to try and improve the results. So now, we will break out our big boy microscope. Say hello to our big boy microscope. This isn't a professional grade instrument, but it isn't too shabby either. We have mounted our converted webcam to this, and we are going to image some of those microchips with this setup. What this microscope does have, is a decent movable stage. And, at the bottom, we have our laser diode. We are using this little M12 to C mount converter, to attach our crappy webcam to this flashy microscope. It does need to be pointed out that our little webcam has an image sensor that is about a quarter the area that this microscope is designed for. Right, let's use this interesting infrared imaging system to look through some of these microchips. The results are far from perfect, and to be honest, this microscope struggles with magnifications greater than 100 times, even under ideal conditions. You can see that at 1000 times magnification, we are getting all kinds of optical aberrations. Some of these are caused by the monochromatic light source. Right, let's take a look at another chip. Our results are hardly laboratory grade, but this is a really cheap webcam, and we are imaging through nearly a millimeter of silicon. For such a janky setup, we think these results are rather marvelous. Well, microchips are not the only thing made of silicon, so we wanted to see if we could find some more objects that are made of this material, and try and image through them. This is a silicon solar cell. It is polycrystalline and certainly not polished, so we are not expecting any optical clarity. Immediately, we can see the rear contacts of this cell being visible as a shadow. It is only when this is pressed right up to that wonderful Project 326 logo, that we can get any clarity. It's not that the light is being blocked by this solar cell, it's more a question of the light being dispersed by its rough surfaces. As we did our research into the properties of silicon, we learned that the band gap is temperature sensitive, and when we plot how strong this effect is, we think it should be visible in a simple experiment. So, let's try it. It's a pretty simple setup. We are going to be imaging through this small piece of silicon wafer, against the reflected illumination. If you watch this piece here, you can see it visibly darken as the flame is applied. Because we are viewing this at the very edge of this band gap, the differences over temperature are more pronounced. Looking directly, we can see how this small piece of silicon appears to darken, and then become more transparent again, in direct response to the temperature. On this channel, we consider this rather crappy and grainy footage to be a successful result of an experiment. I guess we have become too accustomed to our experiments going all shit-shaped. So yes, we probably have low standards. Anyway, regardless of how useless this little camera might be, which probably has zero real-world applications, we are very pleased with the results. Best of all, we learned something new. Last month, we learned the sad news that the famous British YouTuber, Robert Murry-Smith, had passed away. Rob had that everyday man quality of Fred Dibner, but combined with an enthusiastic science teacher. Rob and I had actually managed to become friends, despite a very rocky start. You see, in one of my videos, I had called Rob out on an experiment. Not only that, I had been pretty rude about him too. Later we talked extensively via email, and I quickly realized that he was a true gentleman, and above being petty and resentful. He taught me the value of humility. Rob's YouTube career was prolific. He had nearly 600,000 subscribers, had produced more than 2,500 videos, and had 80 million views to his name. And that was just on his main channel. We had even planned to collaborate on a video. I guess I will have to wait for that one, and it will be on a slightly different platform. Rob's brother has asked that donations be made to a local suicide prevention charity, so the proceeds from this video will be donated to that worthy cause. Rob, the world was a far better place with you in it. Goodbye, old chap. To be absolutely honest, this isn't the most useful thing we have ever made on this channel, but for us personally, we found it to be one of the more interesting projects. Maybe it was because we learned something new, or perhaps it is due to the lucky breaks this project got. I just hope it doesn't mean that the next few projects will be jinxed. We even got lucky with the sunshine, which made my human assistant very confused. Right, let's talk about lookup tables. These are masks that add false color to things like thermal cameras. We have a collection of these that are designed for thermal applications, and applying them can make this camera's images a lot clearer. We avoided using them in this video for fear that it might confuse a few people. Some camera apps like Next Camera also support them. If anyone wants a copy of our lookup tables, just send us an email to the address on screen now, and we will try to reply within a few days. And as for seeing through microchips, that was clearly the highlight of this project. Whilst you can't make out features like transistors or even gates, larger features like memories, analog blocks or bond pads are clearly visible. And, if I don't mind saying so myself, the fact that we could get pretty good images of microchips, without any additional optics, was quite incredible. I can tell you now, we really didn't expect it to work as well as it did. So, all in all, not too bad for a shitty webcam, a filter and a laser diode, that altogether cost us just $18. But, now that we have this little thing, we are going to be looking for other applications for it. If you have any ideas, just drop them into the comments. Good ideas will be welcomed, bad ideas will be tolerated, because the only truly terrible thing in this world is to have no ideas at all. Anyway, that's all we have for you today. We hope you enjoyed our little video, or at least found some parts of it interesting. If you think we deserve it, then please feel free to give it a like. And you could always hit subscribe, if you want to see more content like this. This channel doesn't have any sponsors, at least none that actually pay us any money. But, if you want to support the channel, and help us to make videos, then you could consider dropping us a super chat or even buy me a coffee. We do hope that you managed to learn at least one new thing in this video, and that your investment in time was rewarded. Time is the only truly valuable resource we have. This is still a hobby channel, so we can say what we want, and YouTube's algorithm can go and get f***ed. Thank you for your time. You now have only a very short time to choose the next video to watch.